Hey there. So today we're jumping into the wild, chaotic world of electricity. It's this place full of invisible forces, all pushing and pulling in every direction imaginable. But, hidden inside all that complexity is a law that is just shockingly elegant. A law that lets us find these simple, beautiful patterns in the middle of all that chaos. We are talking about Gauss's law.
Okay, let's just start with a challenge. Imagine you've got a million tiny sources of electricity, like a whole cloud of charged particles. Every single one is creating its own little electric field. So how in the world would you figure out their total combined effect at any single point in space? I mean, it sounds basically impossible, right?
You'd think you'd need a supercomputer just to add up every single one of those forces. And honestly, you wouldn't be wrong. It is a true mathematical nightmare. But what if there was a way to just sidestep all of that grinding work, to see the bigger picture without getting totally lost in the weeds? Well, that's the exact problem we're going to solve today.
To really appreciate how clever the solution is, we first have to understand the hard way of doing things. This is what we call the brute force method, where you just tackle the problem head-on, one tiny charge at a time.
And right here you can see the contrast perfectly. On the one hand, you have the traditional method, Coulomb's law. This means you have to calculate the force from every single charge and then add them all up, remembering to account for their strength and their direction. It gets incredibly messy, incredibly fast. And that leads to this gut feeling on the right. For simple, symmetrical things like spheres, there just has to be a better way. Nature loves elegance, and this brute force stuff, it just ain't it.
So to find our shortcut, we actually need to learn a whole new way of seeing. We need to stop thinking about all those individual forces and start thinking about the overall flow of the electric field. And this brings us to this really beautiful concept called flux.
So what exactly is flux? Well, the key thing is it isn't about the strength of the field at just one point, it's about the total amount of the field that's flowing through a surface. Just picture the electric field as these invisible lines spreading out from a charge. Flux is just a way of counting how many of those lines poke through an area that we decide to draw.
To make this really concrete, think about holding a hula hoop out in a rainstorm. The rain, that represents the electric field. The amount of water that's actually passing through the hoop, that's your flux. Now, if you hold the hoop perfectly flat facing the rain, you're going to catch the most water possible. That's maximum flux. But if you tilt it sideways, almost no rain gets through, and your flux is basically zero. It's the exact same idea for electric fields.
All right, so we have our new tool, flux. Now we're finally ready to see how it unlocks that shortcut we've been looking for. Let's see how this whole thing comes together to form one of the most powerful laws in all of physics. Now, before I just give you the answer, think about this. What if it didn't matter how the charges were arranged at all? What if the only thing that affected the total flux flowing out of a completely closed bubble was the total amount of charge you trapped inside that bubble? Any charges floating around outside? They just wouldn't matter. This idea leads us to our magic tool, the Gaussian surface. And this is so important. It's not a real thing. It's an imaginary bubble that we, as the physicists, just draw in space to make the math work. The trick, the entire genius of this whole method, is choosing a bubble shape that perfectly matches the symmetry of the charge. So for a single point charge, we draw a sphere. For a long charged wire, we draw a cylinder.
And here it is, Gauss's law. It's exactly what we just guessed at. The total electric flux poking out of any closed bubble you can possibly imagine is directly proportional to the total charge you've trapped inside it. It's simple, it's powerful, and it's just so elegant. It doesn't matter if that charge is one big blob or a million little pieces. Only the total amount inside the bubble actually matters.
Okay, now for the payoff. Let's actually see how this abstract idea completely transforms those mathematical nightmares into problems you could literally solve on the back of a napkin.
I mean, the difference is just stunning. On the left, if you want to find the electric field from a charged sphere using Coulomb's law, you are in for some seriously nasty calculus. But on the right, with Gauss's law, we just draw our imaginary sphere around the real one. And because of that perfect symmetry, the whole calculation just becomes simple algebra. And the result is amazing. From any point outside the sphere, its electric field behaves exactly as if all of its charge were crushed down into a single point right at its center. And this really gets to the heart of it all. Gauss's law didn't actually change the physics, it just changed our perspective. By choosing a symmetrical point of view, our Gaussian surface, we made all the complexity just vanish. The answer was there the whole time. We just needed the right lens to see it clearly. So this isn't just some clever party trick for solving physics problems. No, Gauss's law tells us something really deep and fundamental about how our entire universe works.
Its importance is absolutely everywhere. It's the reason a Faraday cage works, you know, that metal mesh that shields whatever's inside from electric fields. It explains why any extra charge you put on a metal ball immediately rushes to the outer surface. And maybe most importantly, it's one of the 4 legendary Maxwell's equations, the absolute foundation of our modern understanding of light, electricity, and magnetism, the whole shebang.
So what's the big takeaway here? At its heart, Gauss's law is a tool for finding simplicity. It takes a situation that looks hopelessly chaotic, and with just a simple change in perspective, it reveals an underlying elegant order. It turns chaos into clarity. And that really leaves us with a final thought to chew on. Gauss's law works by finding the hidden symmetry in a problem. It just makes you wonder, what other profound secrets about our universe are just sitting there, completely visible, if only we can find the right symmetrical point of view from which to look?